Of course, I hope it's going to carry on getting better. I'm the low-impact chair of this session, so I'm intending to say as little as possible and then try and get a crick in my neck as I sit at the front, frantically looking at my iPhone. So we've got a great lineup of speakers. We're going to pick up on some of the threads that emerged through the day yesterday on the developing brain during adolescence and childhood. And we've got three speakers, as you can see from your program: B.J. Casey from the Weill Cornell Medical College, Lawrence Steinberg from Temple University, and Eamon McCrory from University College London. They're each going to talk for about 20 minutes, plus or minus whatever we can get away with. We'll take a question or two and then have a panel discussion at the end for 15 minutes or so before we break. And hopefully their talks will be interlinked, and you'll see the coordination that marks this particular session. As BJ talks initially about the cognitive neuroscience of adolescence and how the developing adolescent brain changes from a neuroscientific point of view, Larry then takes over and looks and examines the implications of that for the criminal justice system, or what the implications might be. And then Eamon provides some contextualization, thinking about how that might impact on the UK system, and also talks about maltreatment and the impact of maltreatment on the developing juvenile brain and criminality. So I hope it'll be an exciting session. I look forward to all of the talks, and I'd like to welcome B.J. Casey to give the first talk.
Oh, so positive today. That's quite lovely. I want to just begin by thanking the National Academy, the Royal Society, also Raymond and Beverly Sackler. I also need to acknowledge Raymond's brother, Mortimer Sackler, and his family who have supported our institute. And then I've just highlighted a few fellows' names who have come through our institute and who I am going to really take liberties and highlight their work and trying to make just a few, I think, oversimplified points, but ones that I think we might be able to get a little bit more traction on with regard to discussion between legal issues and also just basic neuroscientists. From animal and also post-mortem human tissue, we have been able to discover that there are major significant changes from conception to adulthood. But I think what the discussion sort of began to draw us into for today is really where we've been able to start to get traction to link these significant changes to behavior is with the advent of magnetic resonance imaging, particularly with regard to functional magnetic resonance imaging. And I think this is really true in thinking about a period of time in which we're seeing really inflections in criminal behavior. So for the most part, I want to start on or really emphasize work looking at this transition into a period of relative or potential risk. Don't want to psychopathologize it, but think about it in terms of why we might see more criminal behavior during this period. But also think about what are some of the changes that are going on to consider the political ramifications of that in terms of policy, diminished responsibility, and issues that I think Larry's going to touch on, and also Eamon. If we just look at the inflection of criminal behavior, you see that around adolescence is when we're getting peak arrests. And so really I think what these sort of data suggest us is what is going on during this time period in the brain that might explain this inflection in behavior. And this is a topic that's received a tremendous amount of publicity in the media, but usually the media wants to reduce sort of our notions or ideas about why teenagers might engage in risky behavior with often poor outcomes. You know, the three leading causes of death are preventable during this period of time, and it's primarily teens putting themselves in harm's way with suicide, homicide, and accidental death. But to the large extent, the way development is described is adolescents just don't have a mature prefrontal cortex, and that's the, for any Trekkie fan, that's the vulcanized part of the brain that makes you rational, tries to help regulate some of our emotions and behaviors. Most importantly, it's just absolutely key in terms of its function and its connection with other brain regions and helping us guide our behavior for more optimized goal-oriented behavior as opposed to responding in the heat of the moment. Now, if it were just all about this prefrontal region, then very young children should be worse and being engaging in these behaviors even more frequently. And that's not what we see in the U.S. health statistics, either in the mortality statistics that I mentioned or in the criminal behavior that we see. And so one sort of framework that a number of groups are beginning to use is to not only track the development of a particular region that helps us regulate our behavior, like the prefrontal cortex across age, but also structures deep in the brain that we know from non-human primate studies and postmortem studies have less synaptic or changes in the synaptic connections during this period, perhaps at an earlier period in time. And this is also a time where there is pubertal onset, and so you have changes in hormonal influences on the brain as well. So basically what I'm presenting here is an imbalance model where you have slow development of the prefrontal cortex across age, but you may have the functional activation with pubertal onset slightly earlier, and then where you get the risky behavior is this imbalance between the two. So that in the heat of the moment, the brain's hijacked by these more subcortical limbic systems, even though you may know better. That system is taking over. And this gets particularly concerning when we think about earlier and earlier onset of puberty. Even though it's just subtle in age, what that change does is if this is development of that prefrontal, let's call it the cool system, it's going to calm things down. And the magenta is where we're talking about these subcortical emotional centers. If you extend that out, not only do you get a longer period of this imbalance, but you get an exaggerated imbalance between these two systems. So the take-home messages and examples from the empirical data, and I'm going to be grossly oversimplified here, will really talk about development, how this differential development in brain systems can lead to changes in behavior, how social context can further modulate this imbalance. And then third, building on much of the discussion yesterday, I do want to talk about individual variability as well. So most of the developmental work, particularly if we're just talking about structural changes in the brain, let's not even talk about function yet, but work from Judy Rappaport's branch at the NIMH has really been, I think, leading the way in showing how different brain regions appear to mature at different points in time. If you just look at this bottom panel, this is from roughly 5 years of age to 21, and this is looking on top of the head, looking down. Anywhere you see blue is where the cortical thickness has already reached mature levels. So you see that occurring in very basic motor areas that help us move, and also in primary sensory areas, such as those that allow us to hear and see. Areas that then use that information to help guide our goal-oriented behavior show a more protracted developmental course, and you don't see them reaching the mature peaking levels until roughly adulthood. Now, this is just the cortical surface, but when we think about criminal behavior, and when we think about teenagers, we think about desire, fight, flight, and threat, and so it's very important to think about deep structures in the brain that might be changing too. And Terry Jernigan at UCSD, when Elizabeth Saul was training with her, they actually showed you can see, again, these are structural changes from late childhood to adulthood, where you see these fuchsia blobs are areas of the prefrontal cortex that are continuing to change, where you see the gray and blue. These are subcortical, limbic, emotional, reward-related areas that are still showing subtle changes as well. So it's more trying to think about how these systems are interacting as opposed to just a simple story of it's all about one area of the brain. Now, again, these are structural changes, and where we get more traction with the advances in imaging technology is when we've been able to look at functional patterns of activation. And that gets us a little bit closer to understanding how developmental changes in the brain are related to behavior. And these studies are only as good as your behavioral tasks, and if we're thinking about development, really a cornerstone of what's changing across this developmental period is how well you can regulate your thoughts and actions and suppress inappropriate ones, even in very compelling and emotionally charged situations. And so what we have been trying to do in other laboratories too are to come up with tasks that we can use in the laboratory so that we can see how well across development individuals are able to regulate behavior, and then also importantly how that might change in the context of I'll call it appetitive or rewarding, those sort of approach-related context or cues. Now, if I gave each of you in the room a task that measured inhibitory control, there would be variability in that. You would probably perform better than most children in adolescence. But again, I want to come back to maybe not you. So I won't have you engage in this task. But there's a point that I think that we should make when we talk about adolescent behavior, and Larry Steinberg's done a lot of work on this too. Many people use the word sensation seeking and impulse control almost synonymously. But I'd like to suggest to you that they have different developmental trajectories and different underlying neural correlates as well. But let's just look at behavioral performance. If I asked you to, most of these tasks just require you to respond, and then out of the blue, there's a signal that says don't respond. And how well we perform on this task, this is just a plot of several individuals performing it from roughly 5 years of age to over 30. And that we see that children have a really difficult time with this task, and gradually we get better. But again, there are some adolescents that are performing as well, if not better, than some of the adults. So this comes back to developmental change, but keeping in mind conditions or situations or experiences that might be driving the individual differences. Now, most of the time we present the data in the following way, as bar graphs, where it looks like we have this really compelling difference. This is just how many times when we said don't go, you go. Children and adolescents, particularly when you tell them not to do something, it's very hard for them not to go. And we see they make many more errors in childhood than adolescents, and adolescents make many more of these errors than adults. Now, where is this represented in the brain? If you have individuals perform these type of impulse control tasks, one of the areas that comes up time and time again across many labs, and in our lab, Sarah Durston, now in her own lab too, has replicated this, areas in the prefrontal cortex or tightly map on to the developmental changes that we see. So you see more activity in children relative to adolescents and adults, and if you just look at that pattern of activity, this is when they're able to do it well. If you look at how well they're able to do it and see how does that relate to that performance, what you see is when they're performing correctly, they're activating this region more, and that's correlating with their overall performance, whether or not they're making errors or not. And so this is suggesting that if you can see these colors, it's really the children and the adolescents that are having more difficult time here. Again, I always like to show correlations like this because the whole bloody brain can light up when you do these imaging studies. And so it's important to identify those areas that are really tightly coupled with the behavior performance at hand. Now, this is just impulse control, and you didn't see any inflection whatsoever during the adolescent period. So now what we want to do is sort of try to understand, is it something about the way our youth, particularly teenagers, represent reward and incentives differently from younger children or adults that might also play a role here. And again, trying to get at this motivational context, which I'm going to focus on predominantly, and Eamon will spend a bit more time doing the emotional, and I won't focus on our work in this area. But if you just think about the importance of how we process reward and how it can bias our behavior, even without our conscious awareness, there are a number of psychological experiments that have been performed to show how incentives can bias our actions. I'm just going to show you one example from Adriana Galvan from our lab now at UCLA. And this is just plotting how quickly you respond to 3 different stimuli that were associated with 3 different rewards, and unbeknownst to them if they got it correct. And what you see is individuals get faster and faster to those stimuli that predict a large reward. And relative to the large reward, if you get a trial correct and you only get a single coin, what you see happening is significantly slower responses to something that's not giving you the payback you think you deserve when you get something correct. Now, how does this map onto the brain? There are two areas that are very sensitive to reward manipulations. Reed Montague touched on these. They're very dopamine-rich areas. One is in the area of the ventral striatum. It's also been implicated in addiction. And the other is in areas of the prefrontal cortex. I just want to show you the ventral striatum data and what we're seeing in response to reward in children relative to adolescents, relative to adults. So what we see is this exaggerated response when they receive a monetary reward. That's different from children than adults. And that imbalance model that I showed you before, it may be consistent with this in the sense that those areas are still developing here, they're mature here, but you get the imbalance between that emotional system kind of weighing in without any sort of suppression. Now, this finding has been reported in multiple labs. One example is Evelyn Kroon's lab in the Netherlands. And I just want to highlight, I don't know if you can see that data. There's the child data and the adult data, and when you have reward trials, you see that the adolescents activate this region more. This is interesting, but it's also the case that cues, not even the reward, but cues come to elicit that same ventral striatum response. This is a big issue with regard to the addiction literature, too. Cues and context that might signal that craving. And that's been shown by Bea Luna's group, where you see in anticipation of reward, adolescents relative to adults are showing a heightened response. And it's not just with money. Other cues that are associated with positive circumstances, such as happy faces, which is always nice to get a happy face in the audience occasionally, because it's very reinforcing when you're speaking to a crowd. So basically, we see the exact same pattern. This is a postdoc, Leah Somerville's work in collaboration with Todd Hare, also previous from our group. Now, good. Now, if we superimpose this positive information in a task where you're told, no, don't go there. For instance, giving happy faces and now saying that's your non-target. What we see relative to neutral or cold stimuli is that adolescents make many more errors than children or adults. It was actually some of the neuroimaging studies that began to get quite exquisite behavioral paradigms to examine this, so they've helped in that way. As I think Eamon will talk about, you get a very similar response to fearful faces or cues that signal threat, where there's heightened activity in adolescents relative to children and adults. I now want to just turn to social context, and Larry's going to build on this too, and that is what does the social context, because a lot of the criminal activity is amongst peers. So what influence do peers have on these systems and on behavior? And Larry has shown previously and also in a more recent imaging study, just if you look at behavior, if an adolescent versus an adult is playing a video game where they're entering into an intersection where there's a yellow light, adolescents, when there's a peer watching their performance, will make many more risky decisions in terms of whether to proceed through that yellow light, and they'll also result in many more crashes in that game. And that's shown here and here. But it's only when the peers are present. Now, if you look at the pattern of activity that correlates with that, one of the regions that's coming up again is the ventral striatum. So those risky decisions, when the peer is there, is actually tightly coupled with the degree of activity in this region. Now, again, I always like to come back to there's a lot of individual variability, and so even if we just build on Larry's work and we look at what about individual traits of adolescents performing that task, one measure you can get is how resistant they are to peer influences. And when you look at how resistant they are to peer influences, we see that adolescents who are represented here in red, for the most part, aren't showing a whole lot of resistance, and they're activating this particular brain region more. So there's individual variability as well as the developmental. It's almost like a double whammy. Let me just show you one more example of individual differences. If we go back and we look at the pattern of activity to just monetary reward, where we see a heightened response in adolescents, if you then get anonymous ratings of the likelihood of engaging in risk behavior, we see a tight coupling there. Again, sort of this double whammy notion during adolescence. I just want to end with an example of how, as a group, again, I don't want to speak about individual data, but as a group with particular personality traits or individuals who have shown variability in impulse control and other ways, how long-lasting those effects appear to be and what the neural correlates for those are. So I've had the wonderful opportunity to work with Walter Mischel, who developed the delay of gratification task. For those of you who aren't familiar with this task, do I have time to describe this task in 2 slides? Great. So basically, imagine a 4-year-old. Now, these are 4-year-olds that he tested with 2 cookies in front of them. And what Walter told these 4-year-olds is, you can have 1 cookie now, or if you wait until I come back in a few minutes, then you can have 2 cookies. But if you can't wait, then ring the bell, I'll come back in and you can have the cookie. Now, as many of you guess, the 4-year-olds, many of them, before he was even out the door, they were either ringing the bell or they already had the cookie in their mouth, right? But then they just got 1 cookie. But there was another group that was really able not to go for the cookie. But they did it in a different way than we as adults do, perhaps. So there's videotapes of this, and one little boy, he would sit on his hands so that he couldn't. Sorry about that. He would sit down on his hands so that his hands wouldn't reach out and take the cookie. There's another where you see the child completely turn around, right, so they can't see it. And there's this magical little girl who she comes up with a little imaginary friend, and she has a conversation with a friend to distract her from the cookies, right? So the ways in which they were able to regulate their behavior were important. And then there is, probably for this group, a very interesting character who the experimenter leaves the room and he takes the cookie and he licks the inside and then he puts it back together and he puts it on. And we all wonder where that child is today, right? So now we've been able to follow this first cohort 40 years later. These individuals are in their mid-40s. And we know if they were high delayers or low delayers. And what we wanted to do is, again, look at this difference between, is it just impulse control or is it impulse control in the heat of the moment? And what we see when we have a version of a go-no-go task that is, I'll refer to as cold, no really salient emotional stimuli that you're told not to go to, versus more of a hot version, we see no difference between low and high delayers, but we do when it's a hot version of the task. So they're making more errors as a group. Now, when we go and we look at the pattern of activation in the brain in these individuals, what we see regardless of group, but just in terms of performing the task, they're activating the same ventral prefrontal area I showed that has very protracted development, but what we're seeing is both groups are activating it when they have to suppress a response and not go there. So it's very important in terms of impulse control. Doesn't seem to discriminate between the groups. What does is the ventral striatum in response to the sensitivity of these appetitive social cues. So we didn't use cookies or marshmallows. They don't quite do it. But the happy faces were enough to be compelling to change their behavior, and it also activated this area more in the low delayers than the high. So basically, what I tried to give examples of, and Larry will build on this in terms of how they have implications for diminished responsibility and the like, but that prefrontally mediated impulse control continues to develop into young adulthood, but that during adolescence, there's this period of time when emotional centers in the brain appear to be particularly sensitive to environmental cues. These can be positive, as I've shown you, but we also see in the literature they can be threat or negative too. And that in emotionally charged situations, you're going to have a tension between these systems where this more functionally activated or mature region may win out over the prefrontal. But again, to keep in mind that imbalance varies by individuals. And then just to end in terms of diminished responsibility, again, in talking about in the heat of the moment, which is when most of these crimes are committed, and in those contexts where their peers or certain contextual changes are occurring, this is when it's very hard for the adolescent to actually regulate their behavior. And maybe I'll stop there then.
Thank you very much. We've got time for a question or two.
BJ, I was just wondering if you had any occupational outcome data from those kids.
The delay of grad. Oh.
Yeah, I was one more successful, less successful?
Oh, thank you so much, because that was really important. I meant to mention that. So, this has been covered a lot in the media, too. Low delayers not only tend to have a higher incidence of substance use and abuse, you also see higher body mass index, you see higher rates of divorce. There are a number of negative in terms of actual criminology data. We're not sure about that. I just want to then take a step back, just like I don't want to psychopathologize adolescents, because I think we would all love to have that crush that we had for the first time in adolescence. Just because you're a low delayer doesn't mean that you're doomed to have a bad experience and that you can't regulate your behavior. It may be that those individuals are much more likely to explore new options and be a little bit more risk-taking, but we all know in science it's some of the risks that lead to some of the biggest findings that we get, as opposed to sort of the iterative studies. So,
just one more question. And I forgot, my first duty was to remind you all to use the microphone that you're now using.
Thank you. This is a wonderful presentation. One of the things I've always been curious about is differential levels of risk-seeking behavior in different societies. I mean, we don't see the same degree of crime in other societies among adolescents. We don't see the same degree of auto accidents and the like. And so how do we explain those differences, given that presumably the brain development is the same across these societies?
So that's an important question. I should say that the youth here are not special. You see adolescence has a long evolutionary history, and you see novelty seeking in other species as well. It is true that in cultures that seem to, let me even take a step back. I probably should have started by the definition of adolescence is really pubertal onset, and it's a shift from relative dependence on the parent to independence from the parent. And in societies where much earlier they're given much more of a pro-social role in their community, that may be one factor that's implicated. But in the United States, sometimes if it's really independence from the parent, that can go until 30 or 40 years. So.
Right. We'll have more time for questions right at the end, but let's thank our speaker again for a great talk.